You should also be watching some videos about harmonic oscillators. There's a harmonic oscillators part 1, 2, and 3 that I've made so far, and there will be some more later on that you'll be reading as you get into chapters 3 and 4. But this video is supposed to be more about interacting species models. Now, we've looked at that already a little bit at the beginning of chapter 1 when you read about rabbits and foxes and how we can think of something called the predator-prey model and imagine that the foxes eat the rabbits to try to set up some kind of system of differential equations that models their interaction. And you were tested on such systems also. Let's consider that system again. I'll write it down. dr dt, R represented the rabbits. So dr dt is the rate of change of the rabbit population. You'd want to make sure you keep track of things like units. Are these in thousands or millions of rabbits? That would probably be most convenient. And the original equation looked like this. There was exponential growth of the rabbit population, represented by this 2r term, when foxes were absent, when their predator was absent. But there is an interaction term with the predators that causes the rabbit population to decline when there are lots of rabbits and foxes, and that's represented by taking minus 1.2 r times f. Now these numbers, the 2 and the 1.2, are kind of arbitrary. In this case, they're really just chosen so that we get nice equilibrium points. And you don't really have to think of them as having much significance for the example. In real life, you would want to choose your units carefully and find out those parameter values carefully to come up with a model that's any good. But for the sake of examples, we're not worrying about it. The fox population differential equation, df dt, has exponential decay for the fox population if the rabbit population is absent, so I have a negative f term. But then the rabbit-fox interaction is good for the foxes, and so it tends to increase their growth rate. We have a positive 0.9 RF for the interaction term. So that's a system of first-order scalar equations. Two equations, they're scalars. It's first order because we've got first derivatives. These equations are coupled together. Values of r affect values of f, or maybe more precisely, values of r affect how f changes, and conversely, values of f affect how r changes. So it's a pretty complicated kind of interaction. One thing that's very important to learn in Chapter 2 is to learn how to treat this as a vector equation, one single vector equation rather than two scalar equations. Here's the vector perspective. A vector, well, at least a two-dimensional vector, consists of two components. Two numbers, a first component and a second component, and two vectors like that would be equal if and only if their individual first and second components are equal. Now, there are lots of different ways of writing vectors. Physicists like to use I, J, and K. I hat, J hat, and K hat. They like putting little hats above the letters. Sometimes people write vectors as points. Sometimes to emphasize that they're not literally points, like in my multivariable calculus class, in a certain textbook at least, we sort of put like less than and greater than signs around the numbers in the vector to emphasize that it's not really a point, it's to be thought of as an arrow, and that notational distinction makes the difference. In this differential equations book, we don't do that. We treat vectors either as points, we write them as points, or as what are called column vectors. And we'll usually write them as column vectors unless we want to save some space in our writing. In this case, we would take this system of two scalar equations and write it as a vector equation like this. Essentially just put big sets of parentheses around the left-hand side and the right-hand sides individually. Put dr dt and df dt inside the parentheses there. Try to make them look smoother than I have. That's one vector. dr dt is the first component of that vector, df dt is the second component. Use one equal sign, set that equal to a right-hand side vector where I put these things, the right-hand sides of these two scalar equations, into my first and second components of the right-hand side vector, like this. And because two vectors are equal, if and only if the respective components are equal, this one vector equation is equivalent to the two scalar equations. It's just a notational and conceptual difference that is important. We'll see why. One reason it's important is just for notation. It makes it convenient to write equations more simply, especially when you're writing them in abstract form. It saves you some space. For example, if I introduce a vector, call it capital Y, and I'm going to put a little arrow above the capital Y to emphasize that it's a vector. The book makes it boldface. So in the book, it makes it boldface, but when I write it by hand, I put a little half arrow above it to emphasize that it's a vector, because I can't really make it boldface unless I really just do this a lot. And that gets to be kind of a pain. So we just put an arrow above it to indicate it's a vector. If I let that vector have components, R and F, these things are functions of time, by the way. You should realize that when you're looking at these things, R and F are functions of time, and therefore Y, this vector, is a function of time. We will not bother with the of t's all the time. Once I make that definition, then I can write, and if I also define this, capital F vector of capital Y vector to be equal to what I have up here, and I won't bother writing it again. I'll just indicate that with an arrow. I'll take that whole vector that's up at the top there and put it on the right-hand side of this equation. What I've really done is I've defined a function. I've defined a function, capital F vector, which I'll just call capital F from now on, that can take a vector as input, or if you prefer, a point. You can go back and forth between points and their position vectors. If you imagine a point in the plane and drawing an arrow that starts at the origin and goes up to that point, that would be the position vector of that point. And we can go back and forth between points and their position vectors. So I could imagine this as being a point. The point at the tip of the arrow for Y, if I put the base of the arrow for Y at the origin, takes a vector or a point as input and gives me a vector out as output. It's a function of R and F. You could think of it that way, but you could also think of it as a vector function that takes a vector input and gives you a vector output. Such a function in this class is typically called a vector field. A vector field. And the way you want to visualize vector fields is to plot the output vector as an arrow based at the input vector thought of as a point. I'll say that again. You want to plot the output vector as an arrow based at the input vector where you think of the input as a point. I'll show you with the CD-ROM how to get that to generate vector fields. But for the moment, just take that on faith. Once we've got this notation, then we can write the vector differential equation in this way. Keeping in mind that y is a function of t, I can write the left-hand side as dy dt. The meaning we give to that dy dt is just to differentiate each component individually. Y is r and f. Those are the components of y. Those are functions of t. If I differentiate each of those with respect to t individually, it makes sense that I'd want to call that dy dt. So that's really a vector. It's really this vector up here equals the right-hand side. Once I've got the notation for that vector field, I can just write the right-hand side compactly like that. This has some advantages. One advantage is it just takes less writing. to write this. Another advantage that we'll see is that it allows us to really focus in on the geometric meaning of these equations in terms of their vector fields, which are analogous to slope fields, higher dimensional analogs of slope fields. Let's go over to the computer now and get the computer to plot this. We'll focus on the CD-ROM rather than Mathematica. So zoom in on that there. We're going to go down to predator-prey. Click on that. And by default, I've chosen the numbers for the parameters, the coefficients that are on the CD-ROM. They're also the examples from the book. If you zoom in on these sliders down here and over here, you'll see some numbers that the A, which is the coefficient of the R right here, is set at 2. And the B, which is the coefficient of the interaction term, actually negative B is set at 1.2, so the coefficient of R times F is negative 1.2, like I have on the screen by hand. Over here, the C is the number so that negative C is the coefficient of F in the second equation. That's set to be 1. And the D is the coefficient of the interaction term for the second equation. That's set to be 0.9. Those are the exact same numbers that I put on the screen. Now back out a little bit here and look up at the top. We can see that we've got, well, if you look at this box that's right here, that says direction field. If I click that off, then those arrows disappear. But if I click it back on, they come back in there. Why don't you zoom in on those arrows? Right up here. Those arrows, well, up to a scale factor, essentially represent the output of the vector field. They're all scaled down to be shorter than they should be. And in fact, they're all rescaled so that they have the same length. So technically, this is not a graph of the vector field. Rather, it's a graph of the associated direction field. The directions of these arrows are as they should be. Their lengths are incorrect. The lengths are not as they should be. It makes the picture look nicer. That's the reason we do it. What do I mean that these are the output of the vector field up to that scale factor? Well, imagine plugging in any point into the right-hand side of the vector field, the equation that defines the vector field. For example, we can plug in the point, r equals 2, f equals 1. There's a point right about there. Let's see if I can do this in my head. When r equals 2 and f equals 1, thinking about the right-hand sides here, look at the equations there. A is 2, B is 1.2. If r is 2, we get 2 times 2 is 4, minus 1.2 times 2 times 1. R is 2, F is 1, B is 1.2. That's minus 2.4. So 4 minus 2.4 is 1.6. The number 1.6, you with me here? Concentrate. That's the first component of the output of the vector field for the input r equals 2, f equals 1. For the second component, we'd have to plug it into the second equation. C is 1, so we get negative 1 times 1, f is 1. That's a negative 1. Plus, let's see, d is 0.9. 0.9 times 2 times 1 is 1.8. So we get a negative 1 plus 1.8 is positive 0.8. So the output, if I remember correctly, is 1.6 comma for the 1.6 for the first component and 0.8 for the second component. If you look over the vector field picture here now, or the direction field, you don't see a vector whose horizontal displacement is 1.2 and whose, or what was it? Let's see, 1 point, losing track of what things were, 1.6, and whose vertical displacement is 0.8. But you do see a scaled down version of that, where the horizontal component is about twice as big as the vertical component. If you look at that little arrow there, can you zoom in real close? I don't know how close we go. That little arrow there has approximately that property, where the horizontal component is about twice as big, perhaps, as the vertical. Well, maybe not. Maybe it's more over. I guess I'm pointing at the wrong spot, actually. That's embarrassing. It should be over here more. That's better. This arrow looks more like that, or maybe even this one right here. So they're scaled down versions of the correct output. Now, a very key insight in Chapter 2 is that solution curves in this phase plane, and that's what we call it, is a phase plane instead of a phase line. Solution curves in this phase plane are parametric curves where the parameter, in this case, is t. It's a different use of the word parameter. Here the parameter doesn't mean a coefficient. Instead it means time, really. Parametric curves in t that move. That's what happens as time goes by. R and F, their values change, and your point moves around this diagram. And it's going to move it around in such a way similar to something that happens with slump fields. The solution curve is going to be tangent to the vector field anytime it passes through one of the bases of these vectors. So these vectors are going to be tangent to the solution curve. Moreover, the speed of the solution curve that the point moves at will not stay constant. It will change. The speed of the solution curve is actually given by the length of the output of the vector field at any vector it passes through at its base. Because we can't see the lengths of the vectors here, we're only going to be able to tell how long the vectors are relative to each other by sort of keeping track of the speed of the point as it moves around this phase plane. Where it moves faster, that corresponds to vectors that are longer. Where it moves slower, it corresponds to vectors that are slower or shorter. In fact, you can say its velocity vector at any point is given by the vector that it passes through at its base at that point. The length of the vector being the speed, and the direction of the vector being the direction of motion at that instant in time. So ready? I'm going to click one of these points here and we can watch the solution curve. Why don't we start it right here? It should start off by heading toward the right because we can see that arrow is pointing toward the right. There. Ready? 1, 2, 3, click. Slow or fast? Slow. Slow again. There we go. You can see it goes faster over here where the points are a little bit more spread out, and slower over here where they're a little closer together. You can actually see some discrete points there because it's only plotting some individual points. In reality, it is a true curve that actually has no breaks in it. This particular curve is periodic, as we saw before on one of the first few videos for the course. And it's also important, this is a very important thing for the first few sections of Chapter 2, is to understand the relationship between these two graphs. I was focused on this phase plane graph, but you also want to understand the relationship between that graph and this graph. This graph is showing how R and F individually depend on T. So here you explicitly see T on the horizontal axis. You explicitly see the time over here, whereas in this graph, you only can mentally keep track of time. Here we explicitly have it graphed. This axis, well, that's a little bit of a bad thing here because we're mixing up the units for F and R because we're drawing the graphs on the same axis. It's representing the outputs for the solution functions F and R. Both of these curves are, well, they're part of the solution. When you put them together as an ordered pair or as a column vector or as a point, no matter how you want to think of it, that actually gives you a solution when you put them together. The true solution is the parametric curve in the phase plane. essentially the red and green curves here, red being F, that's the one that goes higher in case you're colorblind, and green being R, that's the one that's a little lower there, are really the components, first and second components of the true solution curve. R is really the first component, that would be the green one, and F is the second one. You want to gain skill in going back and forth between these graphs. How should you do that? Well, you keep track of, it's a pretty hard skill. You got to work at it. You try to keep track of how R and F change over time and how they're different from each other. Sometimes it's also helpful to draw in another line in this graph. If I click on this box right here, that's essentially the y equals x line, the diagonal at a 45-degree angle. They call it the F equals R line here. If I draw that in there, and I'll redraw my solution curve, that's somewhat helpful because what it helps you find is it helps you match up the crossing points of the red and green curves over here. Because when this solution curve crosses that diagonal line, that's when F and R are equal in whatever units you happen to be using. And so in this graph, that's where they cross, and that can help orient you as far as where we are in this graph. We're starting here when R and F are both a little less than 1. That's a starting point. They're a little less than 1. As T increases, R increases faster than F as we move to the right, but not very much upward. That's why this green curve is going up faster initially than the red one is. But once we get over here, now we're going upwards more than towards the right. F is increasing faster than R is, and in fact, once we get to this point right about here, R starts to go down because we're moving toward the left, while F continues to go up. So that's where we're in this kind of range. The green curve is going down, but the red curve is still going up. Think about where the peaks are. When we reach this point up here, that's where F is at its highest point. Back in this graph, that's where the red curve is highest. We're right about there. The green curve is pretty low. R is low because this point is pretty close to the vertical axis there. We continue on. R reaches a minimum right about here. On this graph, that's right about there. F is still going down when we're there. But then we start to move back toward the right, so the green curve starts to go back up while the red curve is continuing to go down until we reach the lowest point, which is basically where we started, the lowest point for F, before the cycle repeats itself. We've got periodic solutions here. These solutions repeat themselves at a fixed interval of time. If you look between the peaks, it appears that the period is perhaps about 5 or so. This peak for the green curve is at about 1, and this next peak's at about 6. A period of approximately 5, or if you prefer, a frequency of 1/5 of a cycle per second, if you think of T as in seconds. Although, if it really is a population, T is probably more likely to be in months or something. There are other solution curves. Some that have smaller amplitudes. I'll clear this one out. There's an equilibrium point right in there. I'm not going to be able to find it exactly just by guessing, perhaps, but I'll get close. Pick a point right there, and you see a very small circle. It's actually not exactly a circle. A very small amplitude for the solution curves there. We're near the equilibrium point. There is, in fact, exactly one equilibrium point where the function is really a constant function that's a solution. Kind of hard to find by guessing here. You could use algebra, as you've done in the past, to set the both right-hand sides equal to 0 and solve for R and F simultaneously to find the equilibrium points. This is a nonlinear system when you set the right-hand sides equal to 0. Nonlinear equations like that can have more than one solution, sometimes 2 or 3, whereas linear equations either have none, 1, or infinitely many. The origin ends up being one of them, but we're not seeing that here. Another one is right about there. R is perhaps a little bit bigger than 1, and F is about 1.7 or something like that. Okay? One more example. We can go way out here and get very large amplitude oscillations. Is this accurate or not? I don't know. We'd have to compare it with real life populations to see how accurate it is. It's not going to be super accurate, actually, in most situations, but it does give us a start at trying to model interactions like this. Let me just show you a couple other things real quick to end this video. There are other kinds of interacting species model. Predator-prey is one of them. You can have competing species, and you can have cooperating species. Doesn't cooperating sound better? Well, cooperating is not on here, but they do give you an option for competing species. I'll click on that one. The equations are up here now. X and Y are two species that compete. In the absence of the other species, both of these are growing according to a logistic kind of model. If you can focus in on those equations there, that really is a logistic kind of growth with an equilibrium at 0 and m for x and 0 and m for y. But we do have interaction terms that account for the presence of the other species, and they both have negative signs in front of them. The presence of the other species is bad for either species. If the presence of y is bad for x, and the presence of x is bad for y. Which species wins out in the end? Do either win out, or do they both ultimately end up cooperating in some way? Well, let's see what happens. This is a picture of the phase plane with a direction field on it. Not truly a vector field because these vectors all have the same length, so we call it a direction field, but they get the direction right. Don't worry about the red and blue lines now. I'll talk more about those in another video. We can focus in on the dots. Those are actually equilibrium points. There are actually 3 equilibrium points there that are not the origin. The origin would be one also, but it's not shown to be one. 3 equilibrium points, essentially where the red and blue curves cross and where they cross the x and y axes, though it's only the red one on the x-axis and the bluish-purplish one on the y-axis. Pick an initial condition, what's going to happen? Let's see, I'll pick one way up here in the upper right. Just see what happens. Watch it. Ready? 1, 2, 3, go. See the green curve there? What happened? It went very rapidly toward this middle equilibrium point, but then all of a sudden, it took a detour up toward this upper left one. What does that mean in a practical sense? You should think about how x and y change. Because you're always moving to the left and then ultimately down to the over to the y-axis here, x goes to 0. The x species dies off, sorry to say, and the y species approaches an equilibrium. Down here, y is blue, it's the upper one, x is red, that's down at 0, x has died off, and y is surviving. Will it always happen that way? Well, I'll go back and pick another initial condition. I'm going to pick one a little bit down to the right of my first one. Ready? 1, 2, 3, go! Oh, that was kind of an interesting one. I don't know if you saw it, but it went down toward that middle equilibrium point, and it looked like it was going to stay there. It stayed there for quite a while, but then all of a sudden it veered off toward this bottom one over there, making y die off and x approach an equilibrium. Now x is the red one here, and y is the blue one. So something radically different happened. In reality, there actually is a solution curve that heads straight toward this middle one and approaches it as t goes to infinity. That one solution curve is called the Separatrix, kind of a cool name. It separates the phase plane into 2 regions. One region over here is going to consist of initial conditions where y dies off and x approaches this number at about 380 or so. And the other one, the other region, consists of initial conditions where it's going to go this way and x will die off and y will approach an equilibrium at about 400 or so. So that's kind of cool that you get this kind of behavior in this 2-dimensional system. There's actually a separatrix down here too. Here you had some die-off in both species for a while before Y recovered or X recovered. If you start off with real low initial values to begin with, like down near 0, they both actually grow for a while before one of them dies off. So it's like with this competing species model, if the populations are small, they don't really interact a whole lot, and both species can thrive for a while, but then ultimately one species dominates. You can see it there. One species dominates and the other species dies off. While it's hard to say whether that's realistic or not, it certainly is kind of interesting. And certainly seems maybe plausible. When there are high populations, both die off rapidly at first before one species dominates. When there are low populations to begin with, they both grow at first before one species dominates. And it's very sensitive as far as which species is going to dominate. It's very hard to tell exactly where that boundary is. So that's a kind of interesting thing that you can say with this. The final thing I want to show you very quickly is, let's see. Oh, I forgot the name. I should remember this. Well, the DE Sketchpad is something that you should play with a little bit. But let's see, there was another one that I was thinking of. Quiz, that's a TD, no, not that quiz. Graphing Solutions Quiz. Okay? This is actually something that I could quiz you on in a sense. Maybe not, we'll see. It's practice in trying to graph X versus T and Y versus T if you only see the phase plane. And it's something that's very important to gain skill at, but it's hard. It takes some work. You've got different choices here. Part A is this first choice. Let's choose the slow plot. I'm going to press this button that says slow plot, and we're just going to watch it go. We're going to see a graph. Ready? 1, 2, 3. There it is. Pretty simple graph. It's just heading toward the origin. It's a parametric curve that approaches the origin as t goes to infinity. This quiz, you try to graph x versus t and y versus t individually. X would start off positive and go towards 0. Y would start off negative and go towards 0. Because x decreases towards 0, you move to the left, and y increased towards 0, it moved upward. These do get more complicated. Part B, what does that look like? Ready? 1, 2, 3, go. Why isn't this working? Go. Clear it. Try again. All right, I'll try the fast plot. There it is. I guess I just wasn't patient enough. That one was coming from the origin when t was very large negative number and goes off to infinity as t goes to positive infinity. I wasn't patient enough. All right, let's look at a more complicated one. Part C, let's try that one. Ready? 1, 2, 3, go. There we go. Now this one's curving around. So x and y are changing in kind of a complicated manner together, and you want to try to draw both graphs accurately. And another thing you want to get accurate is you really want to draw both graphs on the same set of axes and see where the maxima of one of them are related to other parts of the graph of the other one, maxima or minimum. So this is something to really work on. Practice this. For the second exam, there are some practice problems from the book that are related to this. It is an important kind of thing if you're really going to understand what's going on with this stuff, and that's the end of this video. Ones that I'm deciding